Hello, my name is Alex Levesey, a senior scientist at Voss Scientific. In this presentation, I will be describing the development of a system for the detection of battle damage caused by electromagnetic attack. In response to an SBIR solicitation from the Office of Naval Research, our company has developed a compact, portable instrument package called ATOM, which provides immediate feedback regarding the status of target electronic systems after irradiation by a high-power microwave weapon. The system, presently at a technical readiness level of 7, is easily deployed by a single operator in less than an hour and is equally at home in laboratory and rugged field environments. The built-in data analysis provides the operator with evidence of battle damage within minutes of the attack, and with further analysis can identify specific targets that have been affected. Voss Scientific has been involved in directed energy research for over 40 years, including source development, diagnostic design, and laboratory and field experiments. Areas of research include high-power microwaves, ultra-short pulse lasers, pulse power, and charged particle beams. During this time, we have conducted numerous laboratory and field experiments at a broad range of facilities, including land, maritime, and airborne. Our team of multidisciplinary experts has provided numerous theoretical and experimental solutions for research in electromagnetics, ranging from high voltage DC to high energy particles. The team includes both experimental and theoretical expertise in mechanical, electrical, and software science and engineering, and high voltage, RF and microwave, optical, laser, and plasma physics technologies. As part of this team, our software engineers continue to advance the state-of-the-art with the recent release of the Chicago Suite, an advanced three-dimensional fully electromagnetic particle-in-cell code designed for executing multi-scale plasma physics simulations on high-performance computing clusters. Voss Scientific is also very active in the Small Business Innovative Research Program, including multiple Phase 3 awards. For example, we received the first Phase 3 in the Air Force in 1991, called DAC, for Data Acquisition, Archival, Analysis, and Instrument Control. This fully commercialized product is used by the DoD, DOE, educational, and commercial institutions. Voss Scientific offers a wide range of available resources, including laser, pulse power, and microwave laboratories, as well as a portable laser laboratory. This facility is a self-contained cleanroom with multiple ports for beam propagation experiments, featuring a roof-mounted port and structure to accept a 12-inch beam director, and it can be easily transported for remote field testing. As the possibility of the battlefield use of a high-power microwave, or HPM, weapon moves closer to a reality, the need to evaluate the often invisible damage caused by these attacks has moved to the forefront. Shown in the upper figure on the right of this chart is a prototype HPM weapon being prepared for use. The lower figure is a simulated attack scenario. The objective for this work is to develop an electronic battle damage indicator, or EBDI tool, for use with non-kinetic HPM weapons and simulators. Rather than rely on visual or behavioral cues, which are typically absent, delayed, or not observable in an electromagnetic attack, this EBDI tool, developed by Voss Scientific, passively monitors the unintended electromagnetic emissions of electronic systems, providing a unique method to assess electronic system disruption or damage imposed by HPM. The solution proposed by Voss Scientific is built on our 40-plus years of experience conducting field tests in harsh environments, similar to the Navy Proving Grounds at Dahlgren and China Lake as used here. Since the system is intended to be deployed near the target location, it must be able to withstand the full power of the HPM attack without affecting its ability to detect the extremely weak emissions from the target. The system also provides a useful characterization of the HPM exposure. The traditional technique used to evaluate the effectiveness of an HPM system in a laboratory environment is for a team of experts to enter the target area after the event and complete a hands-on evaluation of each of the target systems. This process may require 30 minutes or more to complete, and of course it is impossible in an actual attack of an enemy installation. Other battle damage assessment techniques can take hours to complete, by which time any effect from the HPM attack may have been mitigated. The technology demonstrated in this work provides the indication of battle damage in tens of seconds after the attack, allowing rapid decision-making and action before the battle damage can be rectified. The device we have developed and demonstrated is called ADAM, which stands for Autonomous Damage Assessment Module. Beginning in the late 1980s, Voss Scientific pioneered the development of computer-based automated data acquisition, archival, and analysis for single-shot and repetitive single-shot high-power microwave events. Using standardized graphical user interfaces, this software integrated multiple and eventually hundreds of diverse instruments into a single system controlled by a single operator. Physics-based data reduction algorithms were implemented in the software to automatically convert the raw recorded signals into the physical quantities desired by the researchers. The power of this tool has been applied to the problem of detecting and analyzing unintended emissions from target electronics. A fully self-contained prototype has been developed and successfully demonstrated on multiple field tests, which reliably detected changes in target emissions indicative of battle damage. While the existing system is relatively large, a concept has been developed to substantially reduce the size, weight, and power requirements of the system to support the original concept shown here. By reducing the size of the system, it can be disguised and deployed near the target structure, where it can remain for an extended period, collecting data on the target systems. Two different methods have been developed and tested to provide the remote control and data transmission between the remote control station and the ADAM. The technique used in the field test has been a fiber optic data link. Since the fiber optic connection can be made without compromising the electromagnetic shield of the ADAM, it provides continuous control of the system, which was important in the dynamic field test environment. The fiber system also does not require any range approvals for frequency clearance and supports full bandwidth data rates at distances of up to 12 kilometers. The second method of communication is to use an RF-based data link. This technique was successfully tested over a short range using coaxial attenuation to simulate the loss of a 20-kilometer range. The implementation of this in the remote control process involves only intermittent radio contact, just long enough to send the instructions and transmit the data. This was done for several reasons. First, the radios must be protected from the HPM attack. Secondly, it reduces the power consumption. And finally, it minimizes the risk of enemy detection. By using intermittent radio communication, the data can be relayed to a remote operator over 10 kilometers away while maintaining a low probability of detection. In preparation for an HPM attack, an acquisition sequence is initiated either directly by the remote control operator or set to run at a predetermined time. The system runs through the acquisition sequence autonomously, following pre-programmed instructions. Immediately after the attack occurs, the system examines the emissions from the target for any changes and relays the results to the operator. The Generation 1 ADAM, developed in the Phase 2 SBIR work, provides a level of functionality beyond that required for the EBDI concept, and was designed to allow changes and optimization of the hardware systems to maximize performance. For these reasons, the assembled unit, shown in the figure on the right, is substantially larger than a final concept intended for deployment would be. Because of the close proximity to the target, the ADAM is routinely exposed to the full power of the HPM attack, potentially tens of kilovolts per meter. The system shields itself from the attack and protects the sensitive characterization equipment, which is able to measure signals 22 orders of magnitude weaker than the level of the attack. The ADAM chassis is an electromagnetically shielded enclosure, which is part of the multi-level design to provide the isolation required for the system. The enclosure is also designed to be exposed to outdoor elements, including heat, cold, and precipitation. The system has demonstrated its capability at 2 different field tests, one in a cold, damp environment with temperatures near freezing, and the second in a hot, dusty desert environment. The Atom was operated daily for multiple weeks in both tests without issue. In preparation for the field work, the system was tested in an environmentally controlled chamber and operated without fail at over 130 degrees Fahrenheit ambient temperature. The system characterizes the electromagnetic environment immediately before and after an HPM attack and detects changes in the emissions to determine if battle damage has occurred. With additional characterization of the target's emissions, the Atom has also identified specific targets affected and detected when they are returned to an operational state. The figure on the lower right is an example of target fingerprinting and battle damage detection. The upper red trace is what is referred to as the delta spectrum generated by the Atom measurements. A multitude of peaks are visible in this data, which represent the changes between the pre- and post-shock characterizations, indicating battle damage. Prior to the HPM attack, characterization data from many of the target systems were recorded by Atom. The data from 3 of these targets are shown as the lower 3 traces in blue, green, and purple. Examination of these data in comparison with the delta spectrum at the top shows the high level of correlation between the results. A more detailed statistical analysis of the signals shows that the frequency of the signals in the delta spectrum track the target values within 4 parts per million, and the difference in the relative amplitudes of the peaks has a standard deviation of less than 1 dB. These results indicate very high confidence in the determination of the identity of the target sustaining battle damage. In addition to the battle damage mission, the Atom also provides the ability to characterize the HPM attack. 4 independent microwave sensors mounted in different orientations ensure the HPM signals recorded regardless of polarization or attack direction. Since the ConOps of the Atom is to measure effects of a friendly HPM attack, the nominal frequency of the HPM source will be known, and the Atom complexity of this diagnostic is not needed, thus reducing the swap and increasing the battery life of the system. The nominal frequency is all that is required to allow the Atom to automatically provide the measured incident fields. This data provides a full temporal profile of the pulse and absolute measurements of the fields and polarization. This data can then be compared to what was anticipated to ensure the source performed as intended. All of the original performance requirements of the program have been exceeded in the field demonstrations of December 2021 and August 2022. These demonstrations used the TRL-7 brassboard Atom Gen 1 hardware described previously. The only remaining milestone of the Phase 2 work is the assembly and testing of the more compact Gen 2 system. This portion of the work remains to be funded. We anticipate the Gen 2 system would be about half the size and weight of the existing unit and would be ready for testing in about 12 months from the time of funding. The existing software provides full automated sequencing with immediate data indicating the presence of battle damage. Future improvements could automate the identification of specific targets from the battle damage indicator and report on the status of target recovery. The fully integrated Atom has been transported and deployed by a single operator in remote locations, repeatedly demonstrating it can be ready within 1 hour of arrival. This greatly reduces both the cost to operate the system and the impact on the overall test program. By operating exclusively on battery power, logistical site support is minimized, and deployment options are not limited by the availability of a power source. In addition, the broad spectral range of both the battle damage measurement and the HPM characterization systems allow support of almost any target type or microwave weapon system with minimal or no changes to the hardware. The system can be utilized in many HPM testing scenarios at minimal additional costs. The optional microwave or fiber optic communication link provides flexibility to accommodate any test configuration, while maximizing user control of the system and minimizing test turnaround time. The highly flexible software supports multiple operational modes and allows the user extensive control of both the target and HPM source characterization equipment. Finally, the use of commercial off-the-shelf equipment throughout the design, integrated in a flexible mechanical assembly, ensures a low-cost path for future upgrades or customization to support new requirements. The Atom system has been fully demonstrated in 2 field tests and is ready to support future laboratory or field testing. There is also remaining sealing on the existing SBIR contract to develop a more compact covert package, which would be even easier to deploy for remote testing at any location. At present, the software provides a rapid indication of battle damage. Additional software improvements could provide automatic target identification from a library of pre-characterized options. While the system was originally designed for a specific mission scenario, the flexibility in the RF systems will support a broad range of other target and HPM weapons with minimal or no modification. We have demonstrated this technology in previous work as part of an automated effects characterization system. The Atom could be integrated with any existing test facility where its capability can augment existing target damage assessment techniques. This ability to detect target effects through monitoring of unintended electromagnetic emissions has been shown to reduce target evaluation times by an order of magnitude or more. Integrating this with laboratory target effects testing can improve data throughput and reproducibility by eliminating human interactions with target hardware and ensuring consistency in evaluation criteria. When combined with computer control of the HPM source simulator, a fully autonomous effects testing system can operate 24/7 with minimal human intervention. These techniques have been demonstrated on a broad range of targets and can easily be expanded to support new target types. Voss Scientific is seeking partnerships in the HPM testing community for the opportunity to demonstrate the capability of the Atom system. Note that the existing SBIR contract has sufficient sealing to produce a Gen 2 version that could be customized for a different type of target or HPM source. We also are pursuing the opportunity to continue to improve on the Automated Susceptibility Test Apparatus, or ASTA, to apply the ability to complete hundreds of effects test points per day to more asset types and HPM simulator systems. If you are an HPM researcher who is interested in adding a new capability to target effects testing and improving data quality and quantity, or know someone who is, please contact me. If you are planning a future field experiment, we can certainly provide additional capability to your test with minimal impact to the bottom line. Thank you for your interest in this technology.